Hello, everybody. I hope you are doing well. This is my lecture for week 11, session 2. Let's continue chapter 3 and 4 of Jonah textbook for the piping system. Actually, in this chapter and chapter 5, we will go over three different types of, project or, question for the, piping system. The first one is single pipes. So we just studied a single pipe. Single pipe. You already learned, about this part in fluid mechanics. However, here you just learn some actually new methods to analyze single pipes. The second part of this actually section is multiple pipe. We will go over parallel and series pipe, and then eventually the last part we just discussed the pipe networks. So let's go over the single pipes. My two lectures about this, single pipes. Sorry. Look, guys, here you can see three different actually types of problems for the single pipes. Keep in your mind that, guys, we can define different types of problems. Here you can see actually three typical problems for single pipes. For the type 1, actually, for the single pipes, we are dealing with several actually properties and parameters. So, for example, you need to have the fluid properties, you need to have the density and viscosity, we need to calculate the Reynolds number, and then based on the Reynolds number, actually you can calculate the head loss and this thing. We need to have some information for the pipe. We need to have the diameter, length, and the roughness. You need the diameter length to calculate the HL. Also, we need to have the, roughness, to calculate the friction factor. We need to have the flow rate or average velocity, and eventually we may need to have pressure drop or head loss. So for the first, actually, for the type 1 of question, we have all information except the last part, the pressure drop or head loss. This part is unknown, and you need to determine the pressure drop or head loss. For the second actually type, everything is known except the flow rate or average velocity. And then for the third one, the diameter plus flow rate and average velocities are unknown. I'm sorry. So again, guys, this is three typical problems for the single pipe. We may define several other type of problems. For example, you may ask to calculate the density. You may have a problem with the, for example, unknown lengths. Correct. So keep in your mind that this is actually three main example for the single pipes. Now let's go over these different three types of problem, and then discuss this problem in more detail. So for the type 1, the type 1 is the easiest actually type of problem. It's straightforward. We can simply calculate the actually head loss or pressure drop. So when the head loss or pressure drop is unknown, guys, means that diameter is known. So when the diameter is known, you have also the velocity or volumetric flow rate. So you can simply calculate the Reynolds number. Epsilon over D is known, so you can simply find friction factor from the Moody's diagram or from those correlation that we discussed in the previous lecture, such as Chang equation. Sorry. So you can simply calculate the HL, and then by having the HL, you can actually simply you can use the Bernoulli equation to calculate the pressure drop. Right? So this is the easiest one, actually, the straightforward method to calculate the pressure drop. Keep in your mind that in this equation, gamma is the specific weight, it's rho times the G. The other thing is that, guys, for the single pipe, the diameter of pipe is constant. So meaning that the D1 equals to the D2. So if you write the mass conservation equation, you can write m dot 1 equals to the m dot 2. Or density times A1 times V1 equals to the rho 2 VA2, V2. If we assume that we have a incompressible fluid, you can cancel densities, and then you can simply cancel the velocities, in this equation. So keep in your mind that for the single actually pipe with incompressible fluid or constant density, you can simply cancel the velocity term in Bernoulli equation. Okay, this is the easiest one, straightforward. The second type is, actually Q or V dot, meaning, the volumetric flow rate plus average velocity. Both these two parameters are unknown. So when both these two parameters are unknown, guys, let's look at, the actually available information. So diameter is known in this actually type of problems. So when the diameter is known, epsilon over d is known, the relative roughness is known. However, you don't have the velocity. So you don't have the velocity, you can calculate the Reynolds number. So the Reynolds number is unknown. So when the Reynolds number is unknown, you can't use, the correlations or Moody's diagram to find the, friction factors. So F is unknown, in this type of problem. So what you need to do, guys, you need to use the trial and error method to solve this type of problems. How? You need to assume a value for the F. So when you assume a value for F, you need to solve Bernoulli and mass conservation equations simultaneously to determine the velocity. So here you can see the Bernoulli equation and then, mass conservation equations. And then keep in your mind that the HL is a combination of major and minor losses. Then when you find the velocity from the Bernoulli equation, you can calculate the Reynolds number. Now you have the Reynolds number. You already know the epsilon over d or relative roughness. Now you can find the equations or Moody's diagram to calculate the, F. Now, what you need to do, you need to just check your initial actually assumption. So what you need to do, you need to compare this new F with the initial value. If the difference between these two F is less than 0.003, you are good. Otherwise, what you need to do, you need to just repeat this process. Now, this process, guys, depends and strongly depends on your initial guess. If you start with a good assumption, you can find the, actually F after, 2, 3, trials. So the question is that what is the best initial value for this, type of problems? To answer this question, guys, let's look at the, Moody's diagram. This is the Moody's diagram. So here the laminar for the laminar flow, this part is for the turbulent flow. Now let's assume that the relative roughness is 0.002. This one, correct? If you look at this chart, guys, you can see that the actually F friction factor for this specific relative roughness, because the Reynolds number is unknown in this actual type of problem, changes between this value here, which is almost 0.023, and let's say 0.040, for example, 2, correct? If we assume that this is a actually turbulent flow. Now, so it's a good idea, guys, if you select by having the epsilon over d, you pick a value in this range, correct, as the first initial guess. It doesn't make sense to select initial value of F, for example 0.01 for this case, because with a good actually certainly that the F is something between these actually values or in this range, correct? So, but guys, I recommend you to start from 0.023. Why? Because if you select, guys, 0.023 for the F, actually this F represent this area for the Reynolds number. Look, for example, if the Reynolds number is 10⁻⁷, this is your friction factor, 0.023. If your Reynolds number is, let's say, for example, 8 to 10⁷, again, this is this your friction factor. If the Reynolds number is, let's say, 10 to 6, again, your friction factor is 0.023. So I recommend you guys for the second type of, problem. It's a good idea if you start from the friction factor actually represent to this flat, area. Correct? This is the best initial guess for the second type. Now, here you can see, the flow chart, for the type 2 actually problem. So assume F, calculate F, volume, velocity, then calculate the Reynolds number, calculate new F, compare this to new F, and then, make a decision. If this, actually the difference between these two F is less than 0.003, you are good. Otherwise, use the F new and then repeat this calculation. Okay. So this is the first method to solve, single pipes. So also, guys, you can use second method to actually solve type 2 problems. In the second method, guys, you don't need to use the trial and error method. You can simply find, the actually velocity. So how, look, guys, if you can actually plot if the friction factor versus F actually square root of F times Reynolds number, you will see that this actually product is independent of the velocity, and then you can simply find the diameter. How? Here you can see how this method works. Look, guys, we can write HL equals to the FLD times V squared over 2G. So keep in your mind that, guys, this actually, that this equation is for the major losses. If you have minor losses, you need to write the minor losses, in the format of the L equivalent, and then you need to combine with this equation to write it, in this format, FLD V squared over 2G, correct? Now, from this equation, guys, we can find actually square root of F, correct? From this equation. Now, what's the Reynolds number? You know that the Reynolds number is rho Vd times mu. If you calculate this product, if you multiply this Reynolds numbers, to this product, correct? You can see that you can cancel the velocity from this, product. And look, this product is independent of the velocity, correct? So if you plot F, the friction factor versus this product, so actually you can find, the friction factor. So you can find the HL from the Bernoulli equation in this, product, in this actually, equation. So yeah, and then I told you, if you have a minor losses, you need to just write the minor losses in the format of equivalent lengths. So look, guys, here you can see figure 3.4. So this is the chart for F versus, square root of F times Reynolds number, correct? So look, guys, this product is independent of the velocity. You can simply find, this velocity by having the density, diameter, viscosity, and then HL can be determined from, the Bernoulli equation. Look, this is the Bernoulli equation. So for the Bernoulli equation, if you have any, you need to have actually the pressure drop. Pressure drop must be known. So by having the pressure drop, if you have no HA, HR, you can cancel these two types. This is for the, a turbine. This is for the, pump. Then you can simply find, the HF. Keep in your mind that, guys, in most cases, you can cancel the velocity because this is a single pipe. I just explained it, in the previous slide. So from this equation, guys, you can simply find the HL, the head losses. Then you can substitute into this equation to find this product, and then by using table 3.4, and then by having the relative roughness, because the relative roughness is known, guys, in this case. So by having the relative roughness, this product, you can simply find the friction factor. So this is the second actually method. So to solve the type 2 problem, guys, you have two options. You can use the trial error method, or you can use this figure 3.4 to find the friction factor, and then by having the friction factor, you can find actually the velocities. So now, type 3 problems. The type 2 problem, guys, is actually the most difficult, type of problems because everything is almost unknown, in this type of problems. So for the type 3, guys, D is unknown. So in addition to the diameter, either velocity or volumetric flow rate is unknown. In this actually section, guys, I use both V dot and Q, for the volumetric flow rate. I use two different, actually textbooks, so you can actually see either V dot or Q for the volumetric flow rate. So yeah, here, guys, you can see that the diameter is unknown, either velocity or volumetric flow rate is unknown. And then when diameter is unknown, volumetric flow rate or velocity is unknown, then what happened? The Reynolds number is unknown. Also, the relative roughness is unknown, so you have nothing to calculate F. So you can't use, the Moody's chart or equation to find the friction factor. Again, guys, you need to use the trial error method to just solve this problem. You need to assume a value for the F, and then you need to solve Bernoulli and mass conservation equation to determine diameter and velocity. Then you need to calculate F from the Moody's chart or from the equations. And then you need to compare this new F with the initial guess. And then you need to make a decision if this is a good assumption or you need to repeat the process. Now, question. What is the best initial value for the F? Again, guys, because this is a trial error method, and it strongly depends on your initial guess. So if you start from a good initial value for the F, you will be able to solve, the problem, after, 2, 3, iteration. Now, so to answer this question, guys, what's the best value for the, initial guess for the F? Let's look at the Moody's chart, correct? So unfortunately, guys, we don't have the Reynolds number, correct? It's unknown. Relative roughness is also unknown, so we have nothing to actually make a decision. However, if you look at, guys, this value for the F, correct, I recommend you guys to start from an initial value of 0.02 or 0.025 because you are in the middle of this actually chart, so this is probably the best one. So for example, it doesn't make sense to start, let's say, for example, with 0.09 or 0.08. So probably, one of these two value or something between these two value is the best, initial guess. So you can start from the 0.02 or 0.025 or something between these two values, as your initial guess for type 3 problems. Here, guys, you can see, the a flow chart to actually solve type 3 problems. You need to assume a value for the F. You need to calculate velocity and diameter from the Bernoulli and mass conservation equation. You need to calculate Reynolds number and then relative roughness, and then you can calculate the new F, and then you need to compare this new F with your initial guess, correct? And then you can report velocity plus diameter here, velocity plus diameter. Okay. In addition, guys, to this, that was the first method to actually analyze type 3 problems. So we can solve type 3 problem, guys, with no trial and error, with no iteration. How? Again, guys, if you can plot F, the friction factor, versus F 1/5 times Reynolds number, you will see that actually this product is independent of, independent of the velocity and diameter. How? Here, guys, we define a new parameter, roughness number. What is the roughness number? Based on the definition, the roughness number is relative roughness over Reynolds number, correct? Relative roughness over Reynolds number. This is called roughness number, RO. So the Reynolds number is rho VD over mu. So this is the definition of roughness number. Now, so look, guys, here you can see the definition for the roughness number. So if we just multiply this relative roughness, this diameter with this diameter, we can simplify it into this format. Okay, now let's assume that we have circular ducts. Correct. If we have a circular duct, we can write velocity equals the volumetric flow rate over area, and the area for this case is pi d squared over 4. And then we can write velocity is 4 v dot. V dot is volumetric flow rate over pi d squared. And then we can substitute for the velocity into this equation. Correct. If we just combine these two equations, we can write the roughness number based on volumetric flow rate. Correct. Look, now it's independent of both velocity and diameter. So the roughness number based on this definition for the circular duct just depends on the volumetric flow rate. So the other thing is that, guys, HL, this is the definition, for the, head loss. Again, guys, if you have a minor losses, you need to write it based on the L equivalent, and then you need to combine into this equation. Now, let's calculate the F 1/5 from this, equation. So if you use this equation, you can calculate F, 1/5 from this, equation. So now let's use the, definition for the Reynolds number, and then calculate, and then let's multiply, these two actually terms, Reynolds times F to 1/5, to see what happens. So if we multiply, these two products, you will see that, the product, this is the product, correct, for this, actually, term. Now, let's use, guys, the definition for the velocity. Correct. So for the circular duct, again, you can write velocity is v dot over a. V dot is the volumetric flow rate. A is the cross-sectional area. Or you can write it in this format for the circular duct. If we substitute for the velocity from this equation into this, equation, you will see that the final product is independent of the, velocity and diameter. Correct. Look, the actually final product, it just depends on the HL, length, density, volumetric flow rate, and viscosity. So in this case, what you can do, guys, if you plot the roughness number versus F 1/5 times Reynolds number, guys, you can simply use that graph to calculate the F, friction factor. Why? Because this term is independent of velocity and diameter, and in this case, both velocity and diameter are unknown. However, you have the volumetric flow rate, correct? So again, guys, to use this actually term, what you need to do, you need to calculate HL from the Bernoulli's equation. Here is, guys, the chart for the friction factor versus F 1/5 times Reynolds number, and then versus the roughness number. Correct. If you have this product and roughness number, you can simply find the friction factor, and then from the friction factor, you can simply find the diameter and velocity by using the Bernoulli equation. So here again, guys, in this part, we just studied 3 different types of problem for single pipe. The first one was, the pressure drop was unknown. It's straightforward. You can simply calculate the unknown parameter, the pressure drop. The second type, actually, the velocity is unknown. And then the third one, diameter and velocity are unknown. Okay, let's solve 2 problems, guys, from this, section, and then, I will go over, non-circular, pipes. So look, guys, you have actually pipeline to transfer oil from Alaska through, from Alaska through the, Alaskan pipeline. So we have the length is known, diameter is known, and then we have the volumetric flow rate. And then you are asked to find the horsepower needed for the pumps that drive this large system. Now, So to calculate, the actual power required for this pump, guys, let's just check, available information. Look, guys, here you have Q, or volumetric flow rate, is known. The diameter is known, length is known, and then so you can simply calculate the velocity, because you have the volumetric flow rate, you have the diameter, you can calculate the velocity. So velocity, diameter, and volumetric flow rate are known. So this is the first actually type of problem. It's a straightforward one. You don't need to use the trial and error method, correct? So what you need to do, guys, you need to write the Bernoulli equation to find the, actually power required for this pump. So this is the Bernoulli equation, guys. Let's simplify the Bernoulli equation. If you write the Bernoulli equation between the two reservoirs, and so you can simply cancel the pressure, because the pressure is, atmospheric pressure, in both these two tanks. And you can assume that the atmospheric pressure is almost constant in both these two locations. So we can cancel, the pressure. For the elevation difference, guys, we have no information for the elevation difference. So let's cancel this one as well. The velocity, guys, because this is a single pipe, so the actually diameter is constant, and then because the volumetric flow rate is is also constant, and then you can assume that this is a actually incompressible fluid, and then we can cancel the velocities as well. There is no turbine, and there we can cancel the HR, and then we can write HL equals to the HA. So what is the HA? HL? HL is the total losses. It's a combination of major losses plus minor losses. Here we have no information for the minor losses. So you can cancel the minor losses. Moreover, guys, this is a very long, pipeline. It's almost, 800 miles. So probably this is a good idea to just cancel, the minor losses. So if you just combine these two equations, you can write actually HA equals the friction factor L velocity square over 2 dg. So to find the HA, you need to have the friction factor. But keep in your mind that, guys, this HA will be in the meter or in the feet, because this has, the actually length, diameter. So okay, so yeah, what we need to do, guys, we need to calculate the friction factor. So to find the friction factor, guys, we need to have the Reynolds number and also relative roughness. Let's see if we have the relative roughness. We have nothing here. Probably we need to find the relative, roughness. Yeah, keep in your mind that, guys, when you calculate the HA, this HA is actually based on, meter or feet here, based on the feet, and then you need to convert it to the, power. So to calculate the friction factor, guys, the volumetric flow rate is known, so you can calculate the velocity from the volumetric flow rate. Also, gamma is known. Gamma is rho times G, so you can calculate the rho, and then you can calculate the Reynolds number. This is the Reynolds number. What is the epsilon over D? You don't have the epsilon over D. Let's go over here. Let's see if you have any information for the material. Yeah, this is the steel pipe, correct? So you can use the reference table to find the, uh, roughness for this, steel, pipe. So from this table, I found the actually roughness for, based on the feed, for commercial steel or wrought iron, and then we can simply find the relative roughness. So now you have both Reynolds number and relative roughness. You can use either, a correlation, or you can use the Moody's chart to find, the friction factor. So this is the friction factor, and then from the friction factor, you if you just substitute the friction factor into this equation, you can find the HA. A. So this is the HA, guys. I told you this HA is in feet. So what you need to do, you need to convert it to power. If you want to convert, head to the power from the fluid mechanics, if you remember, guys, you can use this equation. You can write H equals to the power over G times density times volumetric flow rate. So you have H, you have G, density and volumetric flow rate, and then you can find the power. So this is the power, guys. Actually, this is the energy that is transferred to the fluid. But you are asked to find the actually power required for the pump. And you know that the efficiency of this pump is 85%. So you can use the definition for the efficiency. If you remember from the thermodynamics, you can write the efficiency is desired output over required input. Here, desired output is power added to the fluid. You already determine it. And then required input is electrical power provided to the pump. And then you are looking for this actually power, and then from here you can calculate the power. Look, guys, this is a very huge power, so probably actually practically you can't use one pump, so probably you need to use some pumps in parallel, probably to just add, or yeah, to just add this uh, you know uh, power, or in series, sorry, not in power, in series. So let's see. Okay, this is the first one. The second one, guys, you are asked to determine the diameter of a steel pipe that is to carry 2,000 gallons per minute of gasoline, and you have the pressure drop and the uh, length of the pipe. The length of the pipe is 100 feet, and this is a horizontal pipe, meaning that the delta Z or Z1 equals to the Z2. Delta Z is 0. So let's look at the available information, guys. Look, the diameter is unknown, so D is unknown. What's about the velocity? Do you have the velocity? Look, guys, we have the volumetric flow rate, but because the diameter is unknown, you can't calculate the velocity. So in this equation problem, guys, both diameter and velocities are unknown. So this is the type 3 problem. Correct? This is the type 3 problem. So to solve the type 3 problem, guys, you learn two different methods, and I will solve this problem by using both those two methods. The first one is the trial and error method. For the trial and error method, guys, you need to set the Bernoulli equation and mass conservation equation, and then you need to solve those correlation simultaneously. So from the table 8.1, I found the roughness of this actually steel pipe, and then let's just look at the Bernoulli equation. This is the Bernoulli equation, correct, for the point 1 and point 2 of this actually steel pipe. Now, so let's simplify this actually problem. So actually you have the pressure drop, so you need to keep P1 and P2, correct? Z1 and Z2 you can cancel because it's a horizontal pipe. Velocity, guys, you can cancel the velocity term because this is actually a single pipe, so diameter is constant, and then because it's a steady state condition, mass the m dot in equals to the m dot out, and then you can just prove that the velocities are the same. There is no actually pump between point 1 and point 2. There is no turbine, and then you can write HL P1 minus P2 equals to gamma times HL. This is the first equation, guys. Also, you can write HL equals to the FL dV square over 2G. If we combine these two correlation, guys, we can write P1 minus P2 equals to the FL rho V square over 2D. Correct? Let's see, guys, if we can simplify it more. If you want to simplify it more, guys, you can write the look, guys, the volumetric flow rate is known. So what you can do, you can actually rewrite this velocity based on the volumetric flow rate and diameter. Look, in this equation, we have two unknown parameters. Diameter and velocities are unknown. However, you have the volumetric flow rate. So you can rewrite this actually velocity based on the volumetric flow rate. How? Look, you can write volumetric flow rate, velocity is the volumetric flow rate over A. And then what you need to do, you need to convert the gallon per minute to cubic feet per second. And then from here, you can write the area is pi d squared over 4. And then you can find a relationship, guys, between velocity and diameter, correct? And then you can substitute, for the velocity into this equation, from this equation. Also, you have the pressure drop. The pressure drop is actually 5 psi per 100 feet. So if we assume that the length of this actually pipeline is 100 feet, and so you have the pressure drop. What you need to do, you need to convert this pressure drop to actually pound per feet square, because right now this is a psi, pound per inch square. So if you convert it to the pound per feet square, you have the density, you have the mu. If you just substitute, guys, delta P from here, also for the velocity here, also L, rho, and these things, you can find a relationship between diameter and friction factor. This is the first equation, guys, that I found, from the Bernoulli equation and mass conservation. Correct. So this is the equation 1. This is a relationship between diameter and friction factor. So look, guys, if you assume a value for the F, then you can find diameter simply from this equation. Let's see, guys, if we can set, other correlations. Also, guys, you can write the equation for the Reynolds number. Reynolds number is rho Vd over mu, and then you already found a relationship between the velocity and volumetric flow rate from the previous lecture, from the previous slide. Look, this is the relationship between velocity and diameter. If I substitute for the velocity in Reynolds number from this equation, look, I just substitute for the velocity. So then you can find a relationship between Reynolds number and diameter. And then the third equation, guys, is, relative roughness, epsilon over d. Now I have three equations, guys. So simply, if you assume a value for the friction factor, you can find diameter from the first equation. Then by having the diameter, you can find Reynolds number from the second equation, and then you can find relative roughness from the third equation. Correct. Here is, the actually flow chart to solve, this problem. So you need to just assume a value for the F. You need to find D from equation 1, a Reynolds number from equation 2, and the relative roughness from equation 3. Now, by having the Reynolds and relative roughness, you can find F nu, and then you can compare this F nu with your assumption. Okay, what is the best first guess, guys? I told you, we have nothing to make a decision, but probably the best value is something between 0.02 and 0.025. So I started with 0.025. This is my initial guess. Then by using equation 1, I found the diameter, equation 2 Reynolds number, and equation 3 epsilon over d. Correct? Now I have Reynolds and I have the relative roughness. I can find the new F. This is the F from the Moody's chart. Correct? Now I need to actually compare this F to make a decision. So the difference between these two F is actually the absolute value is 0.01, which is higher than that acceptable criteria, which is 0.003. So what I need to do, I need to use this new F as an actually new guess, correct? So my second guess is F equals to the 0.0145. So by using this F, guys, I found the new F, Reynolds number, and relative roughness. So then by having the new Reynolds number and relative roughness, I found the new actually F, friction factor. which is 0.0143. And then here you can see the difference is point for the between the new F and the previous F is 0.0002, which is acceptable. So you are good. You can actually report this diameter as the and also you can calculate the velocity by using this diameter, and then you can just report the results. So the diameter is 0.53 feet, and then you can find the velocity from the volumetric flow rate. This is the first method, guys, using the Moody's actually the trial error method to find the uh, diameter. Also, guys, you can use the yeah, this is the value for the um, friction factor. Now, the second method, guys, you can use modify Moody's diagram. You can just actually use this product versus the friction factor versus the roughness number to find the friction factor. Let's actually solve this problem by using this method. So from the previous actually section, you saw that there is a relationship between diameter and friction factor, correct? And also Reynolds number can be written in this format based on the available information. Now, what we can do, guys, we can calculate this product. You have the Reynolds number, correct? And then you have the let's go back here. My bad. Sorry, I don't have it here. Let's see. I think I have it. Yeah, here. Look, guys, you have actually everything here, so you can actually find the this product based on this definition, correct? So you have the value for this product. Also, you need to calculate the roughness number. So again, guys, the roughness number just depends on the uh, some thermophysical properties and volumetric flow rate. Everything is known. And then you can find the roughness number. You have the roughness number, and also you have this product. And then from the table, guys, from this figure, you can find the friction factor. The friction factor is almost 0.0148. If you use this friction factor by using the first equation, you can find the diameter, which is 0.534, which is pretty close to actually results of previous method. So this is the actual two different methods to solve type 3 problems. So what happens, guys, if you don't have the circular pipe? For non-circular pipe, if you have a laminar flow, you can use table 3.5, guys. You can use the table 3.5 to find the friction factor. Just keep in your mind that, guys, in that table you need to use the hydraulic diameter to determine the Reynolds number and also to find the relative roughness. So for both relative roughness and Reynolds number, you need to use the hydraulic diameter. What is the definition of hydraulic diameter, guys? We already discussed force times cross-sectional area over P weighted. In table actually 3.5, guys, you have the definition of A and P for different geometry. So for example, for this geometry, you have A, you have P. You can simply calculate the hydraulic diameter, and then based on the value for the alpha, you can actually use for example, if the alpha is 10, then F times Reynolds number is 51.6 for this geometry. And then you can calculate the Reynolds number, and then from this equation you can find the friction factor. So you can use table 3.5 for different geometry for laminar flow. For the turbulent flow, guys, if you have the turbulent flow, you can actually calculate the Reynolds number by using the hydraulic diameter. So to calculate, the Reynolds number, you need to use the hydraulic diameter. And then what's the definition, for the hydraulic diameter? Again, 4 times cross-sectional area over P weighted. And then you can use either Moody's diagram or correlation to find the a friction factor for non-circular uh, ducts. So then please study table 3.3. This is a really useful table for your project. You can see, the different types of valves, the application, disadvantages and advantages. Thank you so much, guys. This is my last slide, and then we will go over the series pipe and parallel pipes next session. So have a great day, guys, and thank you so much.